My name is Kelly Ramsey. I'm an assistant professor at York University, and I'm the chair of the DLSS selection committee. So we nominated Nancy this year. So before I introduce Nancy, I just be mildly annoying that we are looking for two new members on our committee. So if you're professor, assistant professor, and interested in participating in this committee, please let me know. It's very easy, only a few hours. So easy CV item. Okay, so also apologies to whoever was here yesterday. I had the exact same bio, so not creative enough for a second one. But okay, so Nancy's research has helped shape modern understanding of statistical inference and its foundations through her mastery of statistical reasoning. She's internationally recognized for her pioneering work on likelihood inference, including higher order asymptotics and the development of methods that improve the accuracy of likelihood-based approximations. Nancy has a variety of accolades. There's too many to list, but some that stood out to me were that Nancy was the first woman to hold a Canada Research Chair in statistics. She's held several leadership roles, including scientific director of CANSI, and some of her awards include the COPS President's Award, the SSC Canada Gold Medal, the Krieger Nelson Prize, and the Florence Nightingale David Award. Nancy is also a Fellow of the Royal Society, the Royal Society of Canada, the Royal Society of Edinburgh, and a Foreign Associate of the National Academy of Sciences. So we're very excited to have Nancy give the second lecture today, and I hope you guys all enjoy it.
Thanks, Kelly, and thanks to the committee for inviting me to give this pair of lectures. Today's a little bit more technical, but not too much more, I think, because I feel people are getting a little bit tired already in the term. Okay, so I'm starting off from yesterday. If you weren't here, it's not too important. This was a case control study on the risk of melanoma associated with tattoos. And the investigators found kind of a surprising result that it seemed to be that as the number of tattoos went up, the risk of melanoma went down. But they were quite cautious about this because it was so unexpected. And someone who looked quite carefully yesterday noticed that actually it first increases with one or more tattoos, the risk increases. But as the number of tattoos increases beyond that, it goes down again. So it's really unexpected and probably not too reliable. There must be a lot of noise in the data. But what I wanted to emphasize today was making the step from the scientific question to the statistical question. So the scientific question is clear. The statistical model that's used is logistic regression. They computed odds ratios and 95% confidence intervals. I mentioned yesterday they also used directed acyclic graphs to help them sort out which variables to include in the model. And as I said, their conclusions were quite cautious. The other example I looked at was the heat wave in Europe, another example. And this is the headline that climate change could be said to have tripled the number of heat-related deaths. So the scientific question again, estimate the excess number of deaths attributable to climate change. This is based on simulated data, or rather modeled data. It's from a climate model. The statistical methods and models that are used are epidemiological, and they followed a certain protocol that's set out in a reference paper that I mentioned yesterday. For more statistical topics, they use regression and they use the extreme value distribution and a few other tricks in there as well. And the third one I looked at was the chocolate and diabetes. And the scientific question was whether or not dark chocolate consumption affects the risk of type 2 diabetes. This was a large observational study, prospective, the nurses study. The statistical section, they used Cox proportional hazards models to estimate the hazard ratios and corresponding confidence intervals. And they observed a significant linear trend across 4 groups. I didn't mention it yesterday, but they actually fitted cubic splines instead of just a linear model, but you can see from this picture that the linear model is perfectly adequate. And if they had used a linear model, I don't think the confidence interval would look quite this weird. I think that's a function of the spline fit, but I'm not sure. Okay, so why these models? And there are many other examples that we could have looked at, or problems that you would have worked on with your collaborators or your colleagues have worked on. How do you figure out which model to start with? Sometimes it's motivated by some theory, like in economics, there's a lot of theories about how people behave. And so they might start with a mathematical model motivated by the theory. Or in physics, for example, there's lots of physical models. Might be motivated by the design. The ones that I was looking at yesterday were randomized controlled trials and surveys. I mentioned in passing a regression discontinuity design. That's a kind of interesting natural experiment where you have some particular change in a covariate at a given time and you look at the slope before and after. Often the models are chosen because that's what everybody else does. Right? That's kind of what they do in our field, so that's what we're going to do. Sometimes I've seen several of these where the same lab turns out the same methods over and over because that's what they do and that's what works for them. In teaching, I think we tend to rely on some prescriptions, like if it's a binary response, start with logistic regression and see if that's good enough. If it's a time to event problem, try the proportional hazards model and so on. We have these kind of go-tos that save us some time. If there's repeated measures, use random effects. So there's various examples like that. If we want to think about modeling kind of more abstractly, and I don't think we do think about it enough or teach it enough, it is kind of tricky. You need a kind of arsenal of models at your shoulder. And one of my go-tos for that is the book by Davison. He describes a key feature of the statistical model is that there's some variability and we use probability for that. It's kind of obvious once you've said it, but we maybe don't always stop to think about it. The art in the modeling lies in finding a balance that enables you to answer the questions you're interested in or to formulate new questions, but not to overcomplicate the analysis of the data. Another benchmark for me is the book Principles of Applied Statistics, which has a lot of discussion about how to set up models, how to collect data, and so on, emphasizing that probability models are just an aid. They're not meant to describe the state of nature necessarily, but they're usually an aid to interpretation. And one of the strengths of statistical methods is that you can isolate some of the things you're interested in one part of the model and then allow the randomness in the model to take care of the things that you're less interested in. And sometimes there's very little randomness if you're doing very precise measurements in a physics experiment, for example. Sometimes there's really substantial variability that's going to make it quite hard for you to distinguish a signal, and that's typical in data collected on human populations, for example. So these probability models are very likely to be parameterized, and in this sense, they define a whole class of models. And the parameters could be finite or infinite dimensional. And this largely goes under the name parametric or non-parametric modeling, although it tends to be a little bit, well, this is a little bit too crude, I think, but I'll try to address that later. As I said, ideally one or more parameters represent key aspects of the model for the particular application that you're looking at. And the other parameters complete the specification. I mean, the other parameters are kind of not of direct interest, but they're needed to kind of make the model that you're about to use be some kind of natural representation of the data. And that will always depend on the application. This, I think, sounds simpler than it is. And it's partly why I've been spending time thinking more about modeling and less about the actual details of fitting the models. And this paper by McCullough from now more than 20 years ago, What is a Statistical Model? highlights the difficulties in formulating this in a rigorous mathematical way. And I think it's not well understood. I find it a difficult paper. I don't understand it well myself. But I think it's quite an important paper. So if you happen to be interested in the more abstract aspects of modeling, I could highly recommend it. And one of the simplest examples to illustrate why this isn't all that easy is the Box and Cox model, which you might have seen in classes or in courses. So in this model, some transformation, some power of the response follows a linear model. And the parameter in the linear model that we're usually interested in is the regression parameter beta. But as soon as you allow lambda to be a bunch of different values, like a half power or a squared power or a cube or a 1/3 or even the log, beta's meaning changes completely, because suddenly you're on a different scale, and beta measures things on the x scale, but the y scale is changing quite drastically. If you vary lambda from, say, 0.1 to 10, then the variation in the y's changes quite dramatically. So the beta kind of loses its meaning. And it's not often emphasized in studies of this model. We usually try a few values and think, oh, we should take square roots. That'll make a better linear model. And then we go ahead and, as if we already knew, we should take square roots. And I don't have a particular resolution to offer. I just want to point out that this model looks simple, but it's hiding something, I think, a bit deep about what the meaning of the parameters in the model are. Okay, I'll put that aside for now and turn to a topic I'm more comfortable with, the likelihood function. And the likelihood function is just the density of the data. So that's why I've written here. It's proportional to the density of the data. But I've switched the arguments. So it's a function of theta, and the data is considered as more or less fixed. And so what's the value in switching the arguments? Well, it's just a mathematical trick, or even not even a trick. It's just a different way of writing the same thing. But it focuses your thinking on the inverse problem of moving from y to theta rather than moving from theta to y. Probability classes, we move from theta to y. If the model looks like this, then this is the kind of data we expect to see. In statistics, we've got the data. What kind of parameter values might have generated this data? And likelihood just kind of drives that home that that's what you're doing. So it's a way to turn your thinking, I guess. It's also a convenient way to compare parameter values because you're comparing the values according to how likely they make the data you've observed. And I've plotted a simple likelihood function here on the log scale because it's a little bit smoother. Or, well, it has a slightly different shape on the log scale, and we haven't really changed the meaning of it. And I've made sure that it has its maximum at 0, so I've subtracted off the value at the maximum. Because as soon as we say it's just proportional to the density, then we can only look at relative values of the likelihood for different values of theta. So theta is going across the x-axis here, and this is how the likelihood function looks as a function of different values of theta for the data that I've made up to draw this plot. So if you just had one parameter, you could kind of summarize your inference by a plot like this, although of course we tend not to do that. We tend to use it for summary measures, and mainly because they've turned out to be quite reliable. So here's the likelihood function again, and the summaries that I'm going to concentrate on are the distance between the value at the maximum and the value at some other theta value, or the curvature at the maximum and the value of theta that makes it maximum. I'm just describing in words the maximum likelihood estimator and the likelihood ratio statistic. And I've got down here almost, might have forgotten to mention it. This can be converted to a probability if we start with a probability for theta. So that would be a Bayesian approach to inference, where we can think of this likelihood function as giving us probabilities through an operation where we inject probabilities with a prior distribution. And then the laws of conditional probability will give us a posterior distribution for theta. I'm not going to talk more about that today, but it is a central role of the likelihood function. Okay, so we're all on the same page, I'll summarize a little bit of the asymptotic theory that we rely on if we don't take a Bayesian approach. And it's all based on the fact that once we take the log of that product, we have a sum, and sums usually have a limiting distribution that we get from the central limit theorem. So we take the log, we have a sum, we take its derivative, we have another sum, and we solve for the maximum by setting that derivative equal to 0. And we have, because this is a sum, we might expect to have in nice problems at least a central limit theorem. And that's what drives all the first order asymptotics that we use on a day-to-day basis. So it lets us conclude that the maximum likelihood estimator is approximately normally distributed, and that the likelihood ratio statistic is approximately chi-squared distributed. And we even know the variance, that the statistical modeling includes as part of part of its what Xiaoli Meng calls its bonus. You get to estimate the unknown, and you get to estimate how sure you are about your unknown. And you do that on the MLE scale by looking at the curvature at the maximum. So I've just written those approximations up again. I forgot to say, though, way back here when I took a product, that assumes, of course, the y's are independent. So that's going to be hiding in the background. Now, they might be conditionally independent. We might have a given xi here, so a regression problem, that will be okay. They might be weakly dependent. I'll come back to that point. But for the moment, just to explain it, I'm assuming they're independent. So that's why we get a sum of IIDs. So here I've got not IID, but ID, like independently distributed, not necessarily identically distributed. And we hope we have a central limit theorem, and we can work out the asymptotic variance. And then we get our two approximations. So this, I mean, we use this all the time in applied work. Here's some vanilla output from a logistic regression, and we have a bunch of betas here, or a bunch of thetas, I guess we'll say, 5 of them. And each one has a p-value associated with it, and the p-value either has a star or it doesn't. This is all the very standard stuff. This is just using this result that theta hat's asymptotically normal, and we're using the diagonal elements of this covariance matrix to compute these standard errors. What's hiding here, of course, is if these different estimates, the components of theta hat, are not independent or even uncorrelated, because this matrix may not be diagonal. But we've just extracted the diagonal element. Well, the software has extracted the diagonal elements. So we're kind of overlooking that part of it. If it was diagonal, then we would call the parameters orthogonal, and then we have in some sense, these p-values are more independent than they would be if it wasn't diagonal. So that's this part, the theta hat and the curvature at the maximum. And then if we wanted to check the model fit, if this is binomial data, we can compare what in GLIM modeling is called the deviance from the model with no variables included and no covariates to the model that we fit. And we compare that to a chi-squared, and so that's the other part of the asymptotics. So all of which, just to say, is that we're all using this all the time, maybe not worrying too much if the approximation is a good one or not, or whether the asymptotics applies, but it's kind of like a go-to tool that we have in our toolbox. Of course, I oversimplified because, and I started with the modeling by saying we want to isolate some of the things that we really care about, and we have the other parameters as a kind of filling out the rest of the model. So in that sense, the results that I just talked about didn't actually use the likelihood function in its simplest form, but it used the profile likelihood function. Forget the modified for a minute. Each of these estimates and their standard error is based on maximizing over all computing a profile likelihood that only considers the coefficient of age as the parameter of interest. So we maximize out all the others, and then we could draw a picture like this for the profile, and we use the second derivative, and we get this p-value. And so in each case, that's what they've done. It's a little bit hidden, and we don't usually emphasize it, but it does rely on the profile. There's a slightly different version that is sometimes helpful that makes an adjustment to the profile likelihood that could be implemented to kind of account for the fact that you estimated the nuisance parameters. I won't dwell on that just at the moment. So what can go wrong with this recipe? If this always worked, then, well, we could just tell our scientist collaborators what to do, and they wouldn't really need us. So, well, you probably already thought of lots of things that can go wrong. These approximations might be really lousy approximations. The likelihood might be extremely skewed, or it might be that extremes are much more relevant than the middle, or it might have many modes, for example. And so have you really, if your likelihood function doesn't look like a nice smooth hill, but it looks more like Switzerland, then how do you compare different values, and what theory do you use for that? Most of the models that we want to fit today have quite a few parameters, maybe not too many, but many. Of course, this is a very active area of research where the number of parameters in the model increase with the sample size, which, I mean, it's very active now in the sense that it's called high dimensional inference, sometimes say p greater than n, or p growing with n, or p polynomial in n. This is this very current topic. But in fact, I think all through the history of statistics, as soon as you figure out how to do something with a few parameters, you immediately want to figure out how to do it with a few more. That is, well, I'm not saying that very well. What I mean is, as the data gets more interesting, or as you get more data, your model becomes more complex. It wouldn't make sense to collect a million observations and just compare the sample means, right? That's boring. So as soon as you have a million observations, you can think of all kinds of things you want to look at with those observations. And I think that's been a feature of statistical inference for the last 40 years or 50 years, but it's kind of more apparent now where data is so large and everywhere. I mentioned the irregular, I mentioned irregular likelihood. You could have a very irregular parameter space. Mixture models are the simplest example of that. So this says we have two densities. We don't know which one our data comes from, and so we'll postulate that some proportion of it comes from one density and some proportion comes from another. And if the parameter alpha is on the boundary of its parameter space, then we can't distinguish theta 1 and theta 2. So that's a kind of boundary value problem. We can think of lots of interesting likelihoods that we can't compute, often because we have to integrate over high dimensional spaces. So here I've modeled the distribution of y given some latent variable, and then this latent variable itself might have a distribution, but we don't get to observe it. So our observations are just the y variables, and we have to compute this high dimensional integral in order to proceed. Or we just might have the model wrong. I mean, we might have a whole family of parametric models and none of them are right. There's no theta that gives us the actual true value. So I'm going to spend the rest of the time talking about two of these, but at a relatively high level without too much technical detail. The others are also all interesting, but I don't have time to think about them today, to talk about them today. So so the misspecified model that I'll start with, this goes back again to Cox. An awful lot of things go back to Cox. It's amazing. And he set up the problem as I've just described it. There is some true model, but there's no theta value in our family of models that actually gives back that true model. We go ahead and find the maximum likelihood estimator in the usual way. And you can show that under some smoothness conditions, it'll converge to something. And that something is, in a sense, the closest value that gets you to the real model in terms of the KL divergence. And again, under some more smoothness and some independence assumptions, you can show that this has an asymptotic normal distribution converging to this value, the closest true value. It's not fully efficient because we fit the wrong model. So the asymptotic variance is a little more complicated. Before we just had the asymptotic variance was this I inverse. Now it has to be computed using this kind of sandwich form where you need not only the expected value of the second derivative, but you also need the variance of the first derivative. And they're not the same because they're computed under the true model and we did everything under the wrong model. But except for that, you could just kind of change the inference goal and say, okay, I'll accept that I'm interested in this new parameter theta m0 and then just proceed more or less as usual. And you often see this mentioned in applied work where people will just kind of in passing say we used robust standard errors. And they usually mean they used some kind of sandwich form. So that means they had to estimate a variance and estimate an expected value. Estimating expected values is pretty easy. You take averages. Estimating variances is a little bit harder because those estimates are quite variable themselves, so that these robust standard errors are not completely straightforward to use and not completely reliable, but they've become almost quite common in lots of applications where people feel they're buying some robustness by not using the usual variance estimator, but modifying it in this way. It typically makes the variance bigger, so then you feel a little bit safer because you've allowed for the extra variability. Another approach is to take more flexible inference functions. One that I've worked on is called composite likelihood. So the true model is actually a parametric model. In this case, each observation is d-dimensional. But the fitted model is a simplified version of that, where you pick out some subsets of this d-dimensional vector and work out and multiply the density of those subsets together. It's a little bit clearer to see if we look at pairwise likelihood, which is one example of a composite likelihood. So pairwise likelihood just takes all possible pairs of your vector y and rd and pretends they're all independent and multiplies them all together. Of course, that's misspecified and our usual identities won't hold, so we're going to have to use the inference that I just described for a misspecified model. Another example is an AR1 likelihood. So in this case, we have a time series of observations, and the dependence may go back many steps, or it might be a moving average dependence, but we're going to pretend it's AR1 and just work with that conditional likelihood. That's another type of composite likelihood. But probably the most famous is the pseudo likelihood of BSAG that's used in spatial models, which was a big breakthrough because you could work out a likelihood-like inference function by taking the conditional distribution at each point in space, conditional on the neighbors around there, and then multiplying those together. And you can see that it's misspecified if the spatial distribution is more complicated than that, but it turns out to be very useful, computationally accessible, and because it falls in this class of misspecified models, we know how to do inference. A different direction for more flexible inference functions is quasi-likelihood, where you don't actually have a probability model, but just a couple of moments, like the expected value and the variance. And you come up with an estimating equation for the parameter that you're interested in. Here I've assumed it's the regression parameter. And you don't specify a full distribution at all. So this just gives you an estimate. Now, if you wanted to know how that estimate behaves, like what's its asymptotic mean and variance, well, you don't exactly have a full distribution, so you're going to have to just work it out, I guess. But one approach is to getting around this problem of not having a proper model is to use something called a quadratic inference function, and that replaces this V inverse the variance divider with an expansion in basis functions and leads to the generalized method of moments. And in that version, it comes up a lot in econometrics. I feel I'm not explaining this very well, and I think I haven't looked at quasi-likelihood as recently as I've looked at some of the other pieces, so let me try to explain it again. We start with two moments. We have an estimating equation. If we were lucky, we could integrate up that estimating equation, and that would give us an inference function. And that's the quasi-likelihood. So that's the part I was leaving out. So there is some type of misspecified model that might lead us to this. The problem is when you're integrating up in many dimensional space, the path you go on matters. So that leads to some inferential complications. Something that's probably more important now, or at least more popular now than either quasi-likelihood or composite likelihood, is a set of highly flexible models. Well, I say now, this particular first example goes back a long way to Cox again, 1972. So this is we're using a very precise or well-specified linear function for the effect of the covariates, in this case on the hazard function. So I'm thinking in the context of survival data, and we want to know the probability of failure, instantaneous failure at time t. And Cox suggested to model this with some totally unspecified baseline hazard function, and then that gets modulated by your covariates to either raise your risk or lower your risk. So it's a flexible specification in the sense that this part's parametric and this part is not. Empirical likelihood has the same flavor. We assume that the distribution of y has some CDF, F, and we just make a likelihood function for the whole CDF. And then we're interested in some particular aspect of it, like the mean or the variance or some particular moment or a quantile or an extreme value. And we maximize over a whole family of distributions, but under that constraint. So there's a parametric bit, the constraint, and there's a non-parametric bit, the empirical, the CDF of the data. Semi-parametric regression is another one that seems to be quite popular now, especially in studies in causal inference. So here's a treatment, and we're interested in the treatment effect. And we know that there's a lot of covariates that we need to account for, but we don't want to just say, oh, it's some linear function of all those covariates. We'll let it be unspecified, some smooth function, non-parametric function of the covariates. And maybe we're going to fit this with some complicated neural network or something, but we're going to focus in on this parameter. So these are a sort of collection of more flexible models where we have some parametric bit and then a kind of non-parametric bit. Non-parametric bits are hard to work with because they're infinite dimensional. And in particular, we want to know that the parameter that we care about, the beta, the theta, or the psi, has a stable interpretation across these this semi-parametric setting. Now, proportional hazards regression is very well studied, and it's known that it subject to this modeling constraint, it does have a stable interpretation. Empirical likelihood, the same. I think this is still developing in various versions in the machine learning literature and also in the causal inference literature. An example that's kind of in between these, so I'm not going to let this function be arbitrary, although it's almost the same thing. I'm going to imagine for every I here, every yi, we have an xi, and I'm going to just make a separate parameter, one for every one. So this is going to be kind of like a discrete function on all the values of x, but I'll describe it as a matched pairs problem instead. And because it has a kind of interesting structure that I hope I can persuade you of that in a few minutes. So the simplest possible version, or one of the simplest, we assume we have independent exponential pairs. And in every pair, there's a rate parameter gamma I over psi for the first element of the pair and gamma I times psi for the second. I've just chosen to parameterize it that way. I could have done it differently. I could have said gamma I and gamma I times psi, or there's various different ways you could do it. The point is that every pair has a nuisance parameter, so there's lots of them, n, and every pair has the same parameter of interest. So we should be able to aggregate over the pairs and get information about the parameter of interest. So the likelihood function is easy to write down. This is almost a toy example, and it has all those parameters in it. So how do we get rid of all the nuisance parameters? Well, the way I talked about first was a profile likelihood. We just maximize over all of them. There's a lot of them, but it's easy to do. You could write down what the profile likelihood is. It's just that we have maximized out a lot of nuisance parameters. There's another way that I'll talk about more in a minute. We could take the ratio of the observations, and that gets rid of everybody's nuisance parameter one at a time. So we could just go ahead with that. We could also postulate that these nuisance parameters have some structure in common, usually called random effects, and postulate a distribution for them. And that will be more efficient than either of these two methods if the random effects model is correct. So in this, I've just repeated the whole structure again. We have our pairs and our random effects. And so now the likelihood function just depends on three parameters. I got rid of the gammas because I integrated them out. I integrated them over the gamma distribution. So this example was studied in detail by Batty and Cox in 2020. And the first thing they noticed was that in this likelihood, the alpha and beta parameters are orthogonal to the treatment parameter. So that means that they asymptotically, they'll be independent. So in some sense, that's a good thing, at least for first order asymptotics. We can estimate psi without worrying too much if we've estimated alpha and beta well. But the other thing they noticed was that they're orthogonal no matter what the distribution is. Doesn't matter if it's gamma, it could be anything. They're still orthogonal. Now, if it's not gamma, then you might wonder, well, what are the alpha and beta doing here? And it's a little bit subtle. You have to, well, I had to think about it for quite a while. Maybe they didn't think about it for quite so long, I don't know. But you'd have to go back to that closest wrong parameter that I described in the misspecified model. So we said it was gamma, but it's not. We've got these parameters alpha and beta. If we're wrong, if it's some model M, then there will be some alpha 0M and beta 0M that are what things are converging to. And in that general model, the parameters, again, are orthogonal, and it doesn't, just to emphasize, it doesn't matter what the random effects distribution is, as long as it's well behaved and you can integrate over it. And that leads to a proof that the estimate of the parameter you care about is consistent, even if you have the random effects distribution wrong. So that, they just mentioned that and that, oh, that's interesting, you know, that's that. But Heather Batty and I worked on that more, which culminated in this paper, which I've talked about in the department before, on the essentially trying to see how much this property extends to more general settings and what's driving this particular result. How is it happening, and what's trying to understand the structure. I don't think we got to the bottom of it, but we did find a few things. So again, when can we recover the true value of psi, even when the model for nuisance parameters is misspecified? So this is a little bit different question than what we had before. Before, we had the models misspecified in certain different ways, and we might study what happens under the wrong model. Now we say only the nuisance parameter part is misspecified, but the part we care about is well specified and has a meaning no matter what the nuisance parameter distribution is, or how it's modeled if it's not modeled as a distribution. And we felt that it must be the case that parameter orthogonality was important to this, and that it's true. It is important, but it's hard to verify that in any given example because you have to compute the moments under the true model, and that's what we don't know. But we were able to show that for particular classes of models that are based on groups and have a particular type of symmetry, that then you could be sure that you will be robust to the misspecification of the nuisance parameter. I'm not going to go into the details because it's a little bit cumbersome on notation and so on, but that was the high-level conclusion. Most of the examples that we were able to find seem to involve misspecification of random effects, but we've been looking for examples that are a bit different than that. And it does seem to be connected in some ways to Neyman orthogonality. That's a concept that comes up in machine learning. Okay, so I mentioned I'd look again at the matched pairs briefly. And in this case, I've not modeled with a gamma distribution. I've not done profiling. I've taken the ratios within every pair, and that gets rid of all the nuisance parameters, and now we just have a marginal likelihood, and all this theory goes through. It's fine. There's really kind of nothing to say. But is that robust to misspecification? That is it robust to this model misspecification? So what if the real model was that the rate parameters are not multiplied by something, but something's added to the rate parameter in the two groups? How well would this do? This is wrong because it's got all the wrong parameters in it, right? So is there any sense in which this type of inference is robust to model misspecification? I don't have an answer. That's something we're working on now, and we're just kind of exploring around and trying different examples and seeing what we come up with. Just to emphasize it's a slightly different approach because we're imagining that we're focusing on the interest part as well specified, and we just want to get rid of all those other parameters in some way. Okay, the other one of the other aspects of extensions that I was going to mention was when there's high dimensional parameters, because there's a lot of very interesting likelihood work going on there right now. And I mentioned briefly some work that Yanbo Tang did as part of his PhD thesis. So again, we have our data and our model, and our model parameters have a low dimensional part, the part we care about, and a high dimensional nuisance parameter. One example would be a factorial design in a sort of standard linear model. Another example is a standard regression model with lots and lots of covariates, not more than n. It's a big O of n. That just means p is increasing with n, but not bigger than n. So there's various examples like that, and as I mentioned, if p is fixed as n goes to infinity, then we have these standard results from the profile log likelihood function. So we have our log likelihood function, we maximize out all the nuisance parameters, and we can show if p is fixed as n goes to infinity, that converges to a chi-squared with whatever the dimension of this parameter psi is. And here I've done it as if psi had dimension 1, so that I could take the square root and show that this converges to a standard normal. But Sir and Chen and Candace showed some years ago now that fails if p increases with n at a certain rate. And in fact, w doesn't converge to a chi-squared 1, but to a scaled multiple of a chi-squared 1. And this was for inference in the particular model of logistic regression, and psi is one component of the regression parameter. And what was intriguing about this was that it didn't rely on any of the asymptotic theory that I grew up learning, Taylor series and bounding remainder terms and so on, but rather on the optimization path that you take to get the maximum likelihood estimate. And this multiplier depends on the solution of some equations, the proximal something on the optimization path. So it's kind of an interesting result that's completely different. So there's classical, not classical, and it's just a completely different result. And their picture from their paper shows how different it is. This is if they use the chi-squared 1 approximation. This is when they use their proper approximation with the scale multiple. These are p-values, and it's all simulated under the null, so the p-values should have a uniform distribution on 0, 1. And they do in this right-hand picture, but not in the left-hand picture. The middle is somewhere in between. The middle is a version of the likelihood ratio statistic that's a bit better than the vanilla one. Okay. Well, I mentioned in passing that it's possible to improve the likelihood in a different way. You can adjust for nuisance parameters by making a correction related to the Fisher information. You can also adjust this log likelihood ratio statistic, or more specifically, it's a square root. So I'm in the one parameter interest parameter case. The profile likelihood is chi-squared 1, so its square root is a normal 0, 1. So that's a standard result from our old classical asymptotic theory at the beginning of the talk. But you can make a pretty big improvement in that approximation by adding two quantities that can be characterized. And that's what Yanbo studied, because we know that once we add those two quantities, we get, sorry, I should go back a bit, we get this much smaller error. And so he was investigating how much of that is due to the nuisance parameter and how much of that is due to a kind of distributional improvement. And he was able to show, I'll just put all the results here because it's I'm getting really into the weeds now, but I won't stay there for too long. He was able to show that the nuisance parameter part is essentially of order p over the square root of n. And the other piece is essentially independent of the number of parameters, which kind of makes sense because this is meant to capture the influence of all those extra parameters. So if p is super large, that's not so good, but it does show that the correction in going from R to R star is mainly driven by accommodating the nuisance parameters. And the formula for this correction to R is given here, but you don't need to worry about the details. It's just what it is. Okay. Maybe I'm going to skip this slide in the interest of time. But what do I want to say about this in general? Let me think for a minute. Why did we look at this, and why did I suggest for him to work at this? We know that if p increases with n, we get a different asymptotics. We know if p increases slowly enough with n, we get the old asymptotics. But is there some in between? Like if you've got like 400 observations and 150 parameters, which theory should you use? Can you do as well by using the classical theory as long as you fix it up a bit? Or do you really need to use the new theory? And several other people have looked at this as well, Cosmides and Firth in particular for logistic regression. I don't have an answer. It's just it seemed like an interesting problem to look at. And so that's what inspired us to look at this part. Okay, so I'm going to skip that part. There's another version of the likelihood ratio that's emerged relatively recently that I think is also quite interesting, so I wanted to mention it in passing. And this is simpler than all the things I've been talking about, really, because you just split your data into two subsamples. I forgot my extra bracket there. So you assume we have two n observations, and we just take the first n of them for one purpose, and the other, I forgot a lot of right brackets in this slide. It's because I made the slide about a minute and a half before I came up here. So we use the second half to estimate the parameter, and then we use the first one to create a likelihood ratio. And this leads to what Wasserman called a universal confidence set, which it's easy to show that the probability that this confidence set includes the true value is always at least 1 minus alpha. And it's a straightforward calculation because the numerator and denominator now are independent, because the top one is based on the y. There should be a y1 on this. So the top one is based on an estimator from the other piece but the data from the first piece compared to the data from the first piece for a different value of theta. So it's a split likelihood ratio. So there's quite a bit of work going on along these lines, because you could immediately see many different questions. Well, how do you split? Should you split it in half? Should you use random splits? Should you take a bunch of splits and average? I mean, there's all kinds of different things. And Matthias Durton's group has been working away on this, and they have some quite interesting papers about it. So I wanted to mention that as well as kind of a modern-ish topic in likelihood that hasn't been sorted out yet. Okay, so I'll close with just a kind of overview. The likelihood function, I'm tried to argue, serves as a basis for inference, and this seems inevitable if we're going to use probability models, but there's so many variations that seem to be needed. So, I mean, sometimes when students see theory of statistics for the first time, or even the second time, I think all the problems must have been solved because we know what to do in all these different cases. But it's part of being the endless fascination of being an academic that all the problems are never solved. And as the models get more complicated, we seem to need a more and more sophisticated theory. I talked about marginal or conditional likelihood and higher order corrections. I didn't talk about regularization or other distribution theories or different asymptotic analysis. There's all sorts of computational aspects to it that I didn't talk about. Simulated likelihoods. I didn't talk about model selection. I mean, these are all topics related to what I'm trying to describe that I could have, well, I couldn't have, but someone could have talked about. So what guides us when we have like new problems and more complex models and all these complicated scientific questions? How do statisticians approach these problems that's maybe different from the way other disciplines approach the problems? And I would argue that we rely on the foundations in some sense to approach these problems. So I'm going to close with a few words about foundations. And this is mainly based on a paper I wrote with Cox some time ago now. We wrote that we need an interplay between theory and applications, but that the theory means not the theoretical analysis of specific techniques, but the structure of the models for which you build up a whole set of techniques. It's maybe a little bit obscure what we meant by that, but I think it's a lot easier in a sense to say, oh, if I have this complicated set of data, I'm going to come up with a new method to help my collaborators or putative collaborators if I just dreamt it up. And I'm going to prove that my method is consistent and asymptotically normal and it's better than the other guy's method. That's fine. There's a lot of that and it's important. But a step back from that is how do we figure out what's really driving the structure of the models that we built on? And that has to be tested against applications, but it's different from establishing mathematical results. It's kind of one step back, if you like. So when I started thinking about talking about this part of the field of statistics, I thought, I just wrote down on a list, well, what are the foundations of statistics? And first thing you'd think of is, well, all the math you have to learn before you can do any stats. Or you might think, well, it's the big fight between Bayes and Neyman and Fisher. That's foundations, and I don't want to think about that. Or there's a kind of the nature of uncertainty, which we often don't teach, but there's kind of two ways to think about, at least two ways to think about probability, either as what happens in repeated sampling from a model, or how to quantify my uncertainty or one's uncertainty about the conclusion that one is making. There's lots of very interesting work on the nature of induction. But really, I think mostly about how do you interpret p-values and confidence regions, how are credibility intervals from a Bayesian approach different from confidence regions and so on. That's kind of what I would probably classically, or back in the day, have thought of as foundations before I got more airy-fairy, I guess. And then there's all the topics we teach in advanced courses, which some of which I've touched on today. But again, I keep coming back to Cox, and it is quite surprising how much ground he covered in his work, and I was always discovering new things. He mentioned when he published this book that he was a bit nervous about the impact of the book because he put a lot of Bayesian stuff in, and most people were a bit surprised because he'd often been known as a non-Bayesian statistician. But he said he put in quite a bit, and he was wondering how people would receive that. But he also noted that he'd essentially discarded the Neyman Pearson machinery in favor of Fisher's original approach, and I thought that was kind of interesting. So he doesn't say it exactly in the book, but what he means is the hypothesis testing of reject accept is essentially been discarded. Either p-values or Bayesian posterior probability values, but not accept reject. Well, these foundations provide us a basis for our techniques. They also give us a common language for particular classes of problems. And I think they help to clarify the nature of uncertainty. This is an important point that I think maybe we often overlook. It highlights aspects of the data analysis which are likely to raise difficult issues. You could see this a little bit in that tattoo and cancer. So they thought that the dose response curve would go up. It went up and came down. Well, that's either noise in the data, that could happen, or there's something really funny going on, like it went up and came down. I mean, there might be some structure there, but of course, based on all the digging they did through the data, you couldn't conclude it from that particular study, but you might follow up studies to look at it in more detail. And in some sense, thinking about foundational issues helps you to say, to highlight what you're going to do when these problems come up. Maybe more important, well, suggest strategies I've already talked about, but more important is we don't want to be reinventing the wheel for every new application. We need some kind of basic structure. And I've tried to convince you that likelihood and its many variations provides a kind of way to approach not reinventing the wheel. It's a kind of fallback position that you can start from that helps you to solve new problems. And that's my last slide, but I couldn't resist sticking this in just a few minutes ago because we actually managed to send this book to the publisher about a week ago. So we have 3 very happy statisticians among many, of which I'm one. So I indulged myself by mentioning that because if my talk had a few gaps in it, it's because I was busy with the final stages of this. So thank you very much.
So we'll do a quick Q&A. So first we'll do questions in the room and then on, and if it goes maybe over 15 minutes, maybe after. We'll see. He had first and then we'll go. There's no other mics, so can you just put that?
Hi, Professor Reid. Thank you for the talk. I have a question for when you talk about misspecified model, especially when you talk about the misspecified nuisance parameter part. I remember that you defined generalized consistency and orthogonal, and I think you concluded that we only have consistency when we have a symmetric perm transition, as the example we did for spectral model, but for generalized like a generalized linear mixed model, something like that, we usually do not have consistency. If that's the case, then we sort of using like GOTABI information to fix the information bias. Is it method still valid since we do not have consistency at the beginning?
So for people on Zoom, the question was about the consistency in misspecified random effects models, and in particular in generalized linear mixed models. But so what we showed is that the orthogonality that I described would lead to consistency in certain very restricted settings where you had groups and symmetric parameterization. And that doesn't seem to cover generalized mixed models. But I don't think we proved that. I wouldn't be confident to say that correcting the Gadambi information isn't good enough in a generalized linear mixed model. I think there are results on consistency, but it would be consistent for the nearest wrong parameter, if you know what I mean. Like if you had the random effects distribution wrong, it's like that M model where there's some theta 0 M that your MLE will converge to, and it's consistent for that. It's just so that would be in the category of slightly change your target and then go ahead as if everything was fine. So I'd be reluctant to say you'd be wrong in the GLMM, but it wouldn't fall under the structure that we looked at. So.
One I think related question, I've seen recently there are literatures for like extensive for for example, random components of the it's very difficult graph or like hidden factor models. What's your view on those models? Where how do they relate to the foundation theories? I think there are things that are related that to confidence functions, p-value functions, those kind of things.
So the question was how extended likelihood and what was the other one? Hierarchical likelihoods would relate to this. I'm sorry, I don't have an answer for you. I'm not exactly sure. I think it must depend on the details of the hierarchy. And so I don't think I could give you a blanket answer. I think in some sense, they fall under the category of, okay, we want to use likelihood, but it's not quite good enough for our purposes. So we're going to do some stuff and then hope we're okay. And often in those settings, you check that you're okay for a certain class of models. I guess I'm back a step from that for just thinking more high level. So I'm not sure I could answer. I mean, I think it's interesting, but I don't know what else to say. Yeah.
Enjoy the talk. Having grown up with David Koch's writings as you did, I think I can second your implicit theme. Koch, there's almost none of these topics that I've ever looked at where Koch didn't have something seminal to say. It's absolutely astonishing. And
Yes.
I want to ask you about, though, which goes back to your talk yesterday, is likelihood. Where we run into a lot of problems with observational data in the real world, so to speak, as opposed to things like design experiments, is that likelihoods are basically have to form probability of A given B. And it's the given B where getting that wrong or leaving it out can lead you badly astray. What the B has to do with is how the data were collected. So in a survey, for example, an internet survey, B has something to do with self-selection. And the big problem is that you often don't know exactly how to model the probability of B. Have you got any thoughts about that? David Koch did write about bias sampling, but of course in a fairly well-defined situation of sort of why dependent or outcome dependent sampling.
That's a very important point and a hard question because I hid a lot under the y1 ... yn, and of course in any applied setting it's probably more important to know exactly where the data came from and what the biases are than to do all this stuff that I've been talking about today. But how to approach that from a sort of more foundational point of view, I'm not really sure. Yeah.
I guess conditional likelihood gets you partway there. But the problem again is I guess, knowing.
Yeah.
what that kind of conditioning event is and, oh, okay.
I suppose that there might be some robustness that you might gain from using particular types of composite likelihood that didn't depend quite as much on the sampling design. But I'm really guessing, and it would depend so much on the application, I think.
One question on Zoom. So thanks for the amazing talk. Does the application of the variation of the likelihood in study of some applied models, like compartmental models and epidemiology, help improve the interpretation of the results? Or can we stick to the classic forms for Mars? I'm not sure.
I can, okay. Can I share it with everyone?
I'm not sure exactly. She's asking. If you just right here.
Does the application of variations of the likelihood in the study of some applied models help improving the interpretation of the results? Well, yes, I think so. If you're referring to what I was referring to by variation, because the asymptotic part that I was, the asymptotic theory that I was talking about under misspecified models involved the variance of the score function as well as the expected value of the second derivative. So in that sense, you are looking at the variation of at least the derivative of the log likelihood function, and that's inflating your variance estimate to accommodate for the fact that your model could be wrong. So if that's the same construct, and I'm not sure that it is, then I think, yes, it would be helpful.
Thanks, Nancy. I really enjoyed your talk. I have two questions. The first is I'm really curious about your opinion on eliminating nuisance parameters. So, for example, should there be a correct way to eliminate nuisance parameters? Do you have information about that? I mean, there's profile likelihood, estimated likelihood, integrated likelihood, right? All kinds of flavors of likelihood to remove nuisance parameters. So, on what basis do you feel there's a best way or a true way or
So the question for those on Zoom was, is there a best way to eliminate nuisance parameters? Like, you can maximize them out, you can integrate them out, you can do some other tricks, you can find a conditional or marginal likelihood. Is there a best way, or is there one way that's better than the others? Or could there be such a, I don't know the answer. I feel like there should be a best way, but I'm not sure I know what it is. And I think in some sense, the best way would be, it wouldn't matter if you got the nuisance parameter specification wrong, you still got the same answer. But I'm just not sure how often you might be that lucky. We only know a few examples where you're that lucky at the moment, but that would seem like the best way if it exists.
I'm sorry, no problem. The other question, I was really intrigued by the split likelihood. I haven't seen anything about that. What are some of the major areas do you think that that would be, most relevant or that?
Well, I'm probably the wrong person to ask because I haven't really worked on it. I just saw it and thought it was really interesting. One thing I didn't mention is it's very, very conservative as written, because the confidence is guaranteed to be greater than or equal to 1 minus alpha, and it's often equal to 1. So it might miss important things because it's so conservative. And so a lot of the recent research has been trying to find ways to make it less conservative, but still use the same idea. But I think that Wasserman's original paper, his suggestion was that you could have an arbitrarily complicated way of estimating the parameter theta using some fancy neural network and so on, and it wouldn't really matter what the properties of that were, because all you were going to do is plug it in, and you would still have this kind of guaranteed confidence bound. but it also raises a lot of questions. When I first saw it, I thought it was like amazing and it was going to change everything. And then, but pretty soon after that, Anthony Davison and a student showed that it was extremely conservative in certain settings. And so it's, there's not usually one great answer to all our statistical problems, and this one isn't either, but it is a very interesting approach. Does seem to be quite active work on it right now.
This will be the last one.
Thank you, Nancy, for a nice talk. I have a question regarding the foundation of likelihood, as you mentioned. So it's also related to a previous question that I mentioned there. So if you think about data that collect like internet and in a very kind of like evolving way, that the data set may some time period data set may have some new data that come in. And then it's a very common situation nowadays, data situation. So it's related to the current some concept called concept-driven distributional shift. So basically, the online data distribution may evolve over time as we have new data that come in. So I basically have the question that how do we think about this kind of phenomenon from the foundation of likelihood? So I mean, from the practical approach, like one can always fit some new maybe statistical model onto the new coming data, or kind of use adaptive methods to kind of update the parameters over time. But my question is, how can we think about from a foundational view that we can maybe design a likelihood structure that can better persist over time, that can be kind of adapt to this kind of distributional shift or the online change in the data set?
So another hard question. So the question was, how do we accommodate essentially sequential collection of data where we're always adding new data to the data that we have, and the model might be changing, or the distribution of the data might be changing over time. So we have to somehow accommodate that, and how to think about that from a foundational point of view. And I'm going to have to punt, I think, and say it sounds like a hard problem, and I'm not really sure. I think I would have to think a long time, but I feel like if I went back and looked at some of the foundational principles that I outlined, it would help to think about the modeling, but I have no idea if that's true or not. So yeah, good luck.